group problem 17, travelling flame. Okay, so this is the problem statement. We have to investigate the propagation of a flame around a circular track, as seen in the animation, and how the characteristics of this flame depend on certain parameters. So this can be broken down into two pieces: the changeable parameters and the resulting flame characteristics, our independent variables and dependent variables. So these were then subcategorized into the following properties and behaviours. Additionally, it should be noted that during research, I found that this phenomenon had been investigated once before by the Croatia IPT team, who covered certain parameters, but to maintain originality, I decided to cover the other ones. Okay, so here's how we characterize the terms of flame front, continuous propagation, diffusion, and equivalence flame. So the flame front is the boundary between the unburnt and burnt vapor. Continuous propagation refers to the flame's sustained motion without interruptions. Diffusion is the dispersion of particles due to molecular motion, and the equivalence plane, of course, is referring to the part of the track where the oxygen and the fuel are in equal amounts such that it can sustain propagation. Okay, so here's an overview of my presentation. Onto the preliminary. Here's a photo of my experimental setup. Here's my lovely ethanol rocket, my wonderful tracks. These were 3D printed with ABS plastic and then spray painted with a heat protective coating. Measures induced upon the damage of our unfortunate casualties. I have here flame distance and velocity. We're also recording using a camera at 60 fps on this tripod stand, and a temperature probe measured the temperature change over time. Whenever one of my parameters in my experiment were varied, others were kept constant, and this was ensured through measures I will describe later in the presentation. Okay, so now let's explain the theory behind the flame. First, the horizontal cross-sectional area of the trough is represented in this diagram, with the flame over time shown in this animation. So what's happening is the fuel at the track's base is evaporating, mixing with the oxygen in the air, and the flame front passes through this fuel oxygen-dense area, aka the equivalence flame, emitting CO2 and H2O before catching on the next section and extinguishing behind itself, thus explaining why the flame moves. As this is a combustion reaction, oxygen and fuel undergo combustion to become CO2, H2O, and energy. There are two systems that dictate the flame's behaviour. Firstly, the reactants, the fuel vapor concentration above the track, and secondly, the thermal energy emitted by the flame during its propagation. And finally, the quantitative model of the reaction rate, as reaction rate is dependent on fuel and temperature. Okay, so the following reaction diffusion equation models how the fuel vapor above the track evolves at a given position and time. It captures three competing processes: the vapor production through evaporation, spatial spreading through to diffusion, which is shown here in my diagram as well. It's the red arrows of the oxygen molecules escaping, fuel molecules, sorry, and rapid depletion when combustion occurs. So when the flame passes through, the reaction term resets the local vapor concentration, and this drives the continuous travelling flame propagation. Okay, so similarly, the heat transfer from the flame was modelled using a thermal diffusion equation. It represents the spread of heat away from the flame front, coupling between combustion and local temperature rise, and the losses to the surroundings. Okay, the Arrhenius reaction rate links these thermal conditions and reactant availability to the rate of combustion, as omega is proportional to the concentration-dependent collision terms, which also represent the equivalence plane, and is exponentially dependent on temperature. We can confirm our experimental results follow this by plotting the logarithm of omega against inverse temperature, which yields a linear graph with the negative activation energy over the gas constant and a y-intercept of the logarithm of the frequency factor. So that's nice. Now that we understand the foundational principles, let's look at their physical implications. As this involves parameter adjustment to change propagating flame characteristics, first, we got to achieve a stable propagating flame. To understand stability, let's note the 4 flame regimes. No flame occurred when evaporation was too low to sustain combustion. A standing flame was formed when local vapor supply was sufficient, and there was our sort propagating flame, and also an accelerating flame, as seen here. Okay, to explain an accelerating flame, first, note in the video that the distance that the flame travels increases with each passing flame. This is because the heat released from each flame warms the fuel beneath it, thus increasing evaporation rate and thus fuel density in the air above. This is because the heat released from each flame warms the fuel beneath it, thus increasing evaporation rate, thus fuel density in the air above, and hence increasing the rate of reaction, increasing temperature, and so on. So this becomes a thermal feedback loop, which eventually causes a standing wave. Thus, we come to the conclusion that a cooling mechanism is needed for heat losses to balance with heat emissions in the track. So we put the tracks in a water tray, which has a faster and uniform cooling effect. And this works as our rate of temperature increase reached an asymptote, indicating that the heat produced was equivalent to the heat loss. Additionally, it could be noted that this flame went for about 10 minutes, so it's very effective. Okay, additionally, we measured a constant velocity, which further validates the stability of the flame, as the addition of a cooling mechanism stabilized the flame's reaction rate. On to my experimental analysis. So, already from our qualitative explanation, we can predict that an increase in track height would distance the ethanol and the oxygen, and since combustion can only occur along the equivalence plane, where the fuel is equal to the amount of oxygen, since it can only occur along the equivalence plane, this would decrease the reaction rate. Additionally, an increase in track length would extend the fuel and heat recovery time, thus prolonging the flame life. Finally, we might expect a decrease in the diameter of the trough to reduce exposed fuel surface area, thus decreasing reaction rate. However, an increase in flame speed as the diameter was narrowed was measured. Upon review, this turns out to follow the derived equation coming from the divergence theorem and law of cooling. However, we note that the flames extinguishing at an even, we noted that the flames would extinguish at even narrower track diameters. So, what explains this behavior? Well, a greater fuel surface area does enhance the vaporization rate, and conversely, if the trough diameter gets too narrow, the small fuel surface area combined with the narrow surrounding walls acts as a thermal sink, which quenches the flame. However, when the trough walls are narrowed in this middle distance, the expanding post-combustion gases behind the flame interact with the trough walls to cause a pressure buildup behind the flame, which then accelerates the flame. This acceleration induces fuel starvation, where the flame outruns the fuel vapor's ability to resaturate the track, which ends in extinction. Thus, we ask, how do we lessen this effect? After their experimentation, the Croatia IPT team proposed a theoretical design that would hypothetically give us better control of vapor confinement, and so increases the fuel-flame separation distance, such that less heat is absorbed into the fuel in the track. Thus, the thermal feedback loop is reduced. I then designed and 3D printed the tracks, adjusting parameters to optimize the flame life, as done before. Okay. This enabled for us to experimentally verify the theoretical claims of the track's effectiveness as reducing the track temperature gradients over time. As can be seen, the Croatia IPT track design had 5 times less of the temperature gradient when compared to the original track. So to investigate the impact of fuel thickness, there are 2 factors we need to discuss. First, the fuel heat absorption, and second, the fuel oxygen distancing. As less heat is absorbed by a higher volume of fuel, reaction rate is initially slow, but when the fuel is heated enough, the flame propagation is stable. The contrary is that less volume entails faster heat absorption, which causes a thermal feedback loop. Secondly, as greater fuel oxygen distancing would decrease the width of the equivalence plane, a low fuel height decreases reaction rate, and a greater fuel height would increase reaction rate. Charting the flame velocity in regard to trough fuel capacity verifies that 2 competing effects do occur. As can be seen, the gradient increases and then decreases, with the asymmetry indicating fuel heat absorption is the primary influence. Additionally, the increasing size of error bars can be accredited to the diffusion losses as the fuel height increased, because more fuel would be able to escape the equivalence plane. So to investigate the impact of ethanol concentration, we should predict from the Arrhenius equation that as the ethanol concentration decreases, less ethanol evaporation occurs and thus reaction rate decreases. And we can derive the exact theoretical relationships for ethanol concentration and speed. Plotting the flame velocity over time for different concentrations validates this hypothesis, as higher concentrations show a faster acceleration. And we have a general gradient agreement between experimental data and the model. And it is possible each was slightly below their theoretical predictions because the diffusion losses accounted for in the fuel equation, and it can be seen that this gap widens from 50% to about 80%, which further justifies that, as it would be more likely. Additionally, the vapor replenishment was measured by measuring the time in between flames, thus how long it takes for the stoichiometric vapor mixture on top of the flame's trough to sustain the flame, which was found to decrease as the fuel concentration increases. Now on to my conclusion. So here is an evaluation of my report. So diffusion of the fuel vapor was a significant limitation in this experiment and was correlated with the velocity scatter in the fuel height graph. Also, the track temperature was only measured at a point which would entail accuracy concerns. However, the Johannes equation focuses on ambient temperature and therefore it doesn't make it crucial. Furthermore, temperatures within a room temperature range could not be independently controlled, only monitored due to experimental constraints. Additionally, several innovations were produced to thoroughly investigate the phenomenon. For example, I designed a rectangular track to isolate the impact of fuel height and concentration. I've introduced a cooling mechanism based on the premise of balancing the heat and losses as outlined in my thermal diffusion equation. And additionally, we were able to produce and experimentally verify theoretical models suggested from our research. So in conclusion, we have investigated how key parameters, temperature, fuel concentration, layer thickness, and track geometry influence flame speed, stability, and lifetime. We have identified a coupling between thermal absorption and design, and extended the model by regulating the thermal feedback loop using a water bath and improved track designs. Flame acceleration was further influenced by track geometry, where warm narrowing induced flame starvation. Beyond this, we examined geometric limitations and reaction rate effects arising from the wall height and fuel oxygen separation. Thank you.
Nevertheless, I have some questions. First of all, how did you ignite your flame?
Pardon?
How did you ignite your flame?
By lighter.
So you just placed the lighter near it and then it just was ignited?
Yes.
Thank you very much. Then how did you insert the fuel inside of the ring?
We used a pipette.
And did you use any other fuels except for the ethanol?
Yes, we did. Would you like to see it?
Just to clarify. Thank you.
Okay.
And then, did you ensure that how did you ensure that the layer height was staying consistent along the ring?
The wave height.
The layer height
Layer height.
of the fuel.
What do you mean?
Did you ensure that?
They were 3D printed, so.
Yeah, but you were inserting the fuel inside of the pipette. Did you ensure it in any way?
Yeah, we dispersed it evenly across.
Okay, thank you very much. Then how did you measure the temperature?
We used a temperature probe.
Okay, and did you ensure that it was the same?
That was the same.
The temperature, because I think you were placing it in the water
Oh,
bag,
no,
so
the
that was to ensure that the temperature was the same.
The temperature did increase during
Okay, and then how did you?
and I reported.
Okay, and the measurement of the temperature over time, that was at one point of the ring.
Yeah, I also introduced cooling mechanisms and different track designs to mediate the temperature effect.
Thank you very much. And how did you track the flame?
Track the flame?
Yeah.
Using tracker software.
Okay, and how many frames per second did you use?
60 FPS.
Thank you
As I
very
said in my experiment.
Also, the lines we've seen in experiments and I think theoretical comparison, is it like some just proportionality? Is it a fit or is it your theoretical model?
Which are you talking about?
I think in all of the plots you have just some like proportionality shown. Is it the theory?
I'm pretty sure it's the Arrhenius equation.
Okay, but you just like solved particular numerical equation and then put the result inside of it?
Yes.
Okay, and in all of your cases, was the flame always propagating only in one direction?
No.
So could you see some other things happening? I'm sorry, I don't think we have time, but we will discuss it later. Thank you very much.
Sorry.
I think it was not so.
The computer is
Excuse me, guys, could you keep the volume a bit down? We need to focus.
Yes, test, awesome. Then everything works. Then I'm also ready to start. So, hello, my name is Nikita, I'm from Team Germany, and today I will be opposing the problem number 17, traveling plane. We all know the problem, so we can just skip over it. Our expectations for the phenomenon would be that we would see a clear explanation for the propagation of the flame itself, and also the conditions for the stable propagation. Then we would also like to see an experimental setup, which is suited to see that the phenomenon occurring itself, with reproducibility showed, to quantify the traveling speed itself, and also the flame properties. We also would like to see some theoretical model predicting the velocity of the flame, and also the thresholds so that we can see the same limits between the experiments and the theory predicted. And in our opinion, the relevant parameters is the rings geometry, as the radius, depth, also the parameters of the fuel, and of course the temperature together with the concentration of the oxygen. Overall, I would say that we really like the definition of the key terms in the task, and also from that we've seen a very concluding basic explanation describing why the phenomenon occurs with the disbalance of the fuel and the evaporation of it, and then the burning over. So we really like that. We've also seen a lot of experimental investigation of the velocity over some of the key parameters, such as coil geometry, and also other things presented. Nevertheless, we've seen the theoretical model, which was very presented fast, and also it was pretty hard to follow. And most point which we didn't like is that this fine directionality wasn't really explained. So in our case, we think there are some of the cases where the flame doesn't propagate stably, and we would like to discuss these conditions later on. So moving on to the experiments, we've seen that the circle tracks parameters were regarded, and we've seen this parameterization all together with some optimization for the later parts, which we really liked. We've also seen a very wide parameter investigation with the independent measurements for the geometry, also for this measurement of the temperature, and other parameters. We've seen the preliminary verification for our theoretical approach, so that we can see that the assumptions made could be justified, and we've seen this kind of heat protective coating, which we find is a good idea to try to protect the plastic inside of the ring from the deformation due to the temperature. Nevertheless, we didn't really see any verification for that, so that because we know that the ASA is very temperature dependent, so we would like to see some investigation on that. But overall, we would say that our most important points are that the ignition process in our case was unreliable, so just using a big lighter can influence the phenomenon in many ways, and we would propose a particular, for example, an electrical igniter to kind of a full controller. Then we also didn't really see any tracking on how was the tracking of the flame done, not explaining if the flame front was tracked, and other things. Moving to the theoretical, we've seen the modeling of the flame and fuel with the evaporation, diffusion, and reactions rate, which is actually very impressive in case of this kind of a phenomenon. And we've seen some of the explanations of some trends using the visualizations, and as we think the trends from the theoretical approach. Nevertheless, we didn't really see any quantitative comparisons from the theoretical data, and I think this theory wasn't really used on, as was also clarified, and we will be discussing that later on. We also didn't really have the confirmation of the reaction rate assumed in the theory, also unclear the filling of the tube itself, so we have some uncertainties in the volume and also in the flame, which in our opinion should be accounted for and wasn't really taken into consideration. And also overall, we think that we have some contradiction between the experimental coexistence shown and the theoretical trends. So overall, we would say that the task was mostly fulfilled, as we've seen some modeling of the flame and also very wide parameter investigation, and with some sufficient explanation of some trends. Nevertheless, we didn't see all of the characteristics of the flames being investigated, and our main critic point is that we didn't see any quantitative comparison between the theory and experiments, but like the theoretical model was there, and some of the explanation, the basic explanation of the flame was not shown. With that, I would like to invite you to the stage, and I would like to start at the beginning. So you explained for us in the basic explanation that we have this fuel and we ignite it, and then like after its ignition, like the fuel that's produced. We need some time to evaporate again so that the ignition happens, right?
That's right.
Okay. But I think you didn't really quite touch on the point why we actually have only one flame called propagating. Because you've been showing us...
Actually touched on a very interesting phenomenon. Actually, when you ignite a flame,
I think
when you ignite it on a circular track like this, if you were to have an ignition source here, of course the flame would go both ways, because, you know, there's fuel both ways, and that's where the equivalence flame is. Which is actually why I designed a rectangular track, such that I could only ignite one side and it would only go one way, because otherwise I had to wait for an imbalance in the reservoir to ignite.
Yeah, but I think that would be kind of contradicting to the problem itself, isn't it? So I understand you have this like experimental limitation, but like the task states specifically that we have continuously in a ring shaped.
Okay, well, this was just to investigate the certain parameters such as the concentration of ethanol. I did investigate circular tracks, Croatia's IYPT model as well, theoretical model.
So can you maybe just state me the conditions for just one flame front propagating through the ring and not several ones?
Sure. Okay, so if I were to ignite it from here, right, the flames would travel this way and this way, and they would travel at equal velocity because it's the same track, right? I'd then move my lighter this way and stop the flame here.
So you need to extinguish one of the flames on the flame fronts to be precise.
Or you have to wait for an imbalance in the reservoir, but that would also cause temperature limitations.
And like during your parameter variation, we've seen like some of the velocity measurements and so on. They were taken with this linear type of the flame, or they were with the ring one.
They are taken as linear, but
so you mostly investigated all of your parameters with the
this is how I measured it using Tracker, and additionally for parallax error,
I think that's not really on my problems. Can we maybe just go back to the ring problem? So like in most of your parameters, you did the variation with the straight line, yes?
In certain parameters. So
in certain. So can maybe
for example, ethanol concentrations, because and additionally for accelerating flame, I did it.
Yeah.
For fuel layer thickness, I did it because it was much
in a straight line.
In a straight line. That's correct.
But like the velocity then shown in this graph is not the angular velocity, it's just the normal the velocity of the flame going forward.
Yes.
Okay. So in my opinion, that would be that.
Wait,
yes.
What do you mean by angular velocity?
I think in some of the graphs you stated some of the angular velocity. Okay, and maybe let's just finish this point and then I'll move on to the one I mean further. So my opinion that would be that yes, the steel kind of shows the phenomenon itself. I think maybe some of the preliminary experiments with this kind of a setup would be applicable. In our case, the task specifically asks unfortunately for the ring itself. So I think it's sufficient way.
But these were necessary to investigate the behavior.
Exactly. That's why I mean like the preliminary. I think it's very valid what you did.
Yes.
But like in case of a ring, I would like maybe propose you because as you still need to extinguish or create some kind of a disbalance in order for one flame to travel. Maybe just create some ignition mechanisms with a small cap.
What would you propose instead to investigate these parameters using a circular ring?
Exactly. So I just would like to see a starting mechanisms where you probably just like pull things.
Try certain mechanisms actually. I 3D printed paddle pop sticks that not paddle pop sticks.
I understand.
But like sticks that I put in. But the problem was that it would actually absorb the ethanol and then the stick would catch fire because it's
Okay, I understand. That's not the most optimal. But I think like this could be a possible point for improvement in our case. So yeah, but just move further. You are stating maybe to the back to the tracking. You're measuring the velocity. First of all, is it like the average velocity or
the velocity over time.
over time?
Yes.
So, but like in your point in the graphs where you did the parameter investigation, we had on the y-axis we had the velocity. Is it the average velocity?
No, it's velocity over time.
So, but like
Wait, which
how
one
can
are
you
you referring to? Are you
just
referring
like
to
some, for example,
this one is velocity over time. It's average velocity. I
So
used that in
average,
the
okay.
system where I had
Thank you.
like gotten a constant traveling plane as opposed to an accelerating plane. However, when I was trying to optimize to reduce acceleration, I did ensure that velocity over time was measured instead because that's acceleration.
Okay, that will be my third question because in case we're looking at the average velocity here, it will be important to know the velocity over time graph. As you mentioned, so like just looking at the plane front propagation of over time and if its velocity staying constant. So was it constant over time?
No, it was not for narrowing trough diameters such as this.
Okay, that's exactly what
This
we
was
said.
actually explained in the equation that was derived from the Stevens theorem.
May I ask why the velocity is not continuous over time, or why we have separate points?
Oh, because as I explained in my presentation, the trough's width actually impacts the acceleration of the train, of the flame, because the walls surrounding it act as a heat sink, and also as you increase the trough diameter, there is intuitively more fuel at the base.
I think you quite this to my point. Why didn't you, like you said, you track the flame front? So like I would expect that you have just like a continuous velocity over time graph.
Okay.
So why do you have separate points on that?
Separate points on this.
Because like in case of your tracking, we would just see kind of motion.
I'm not sure.
Okay, then just maybe let's move on.
Okay.
In this case, let's maybe stay on the theoretical plot, not on the plot with the parameter range.
Oh, yeah, sure.
Yes, so we see these lines, which I also asked about in the clarifying questions. Are this the theoretical model? Are the predictions? Are they just trends taken?
Derived from that equation.
But it's just the proportionality? Or did you input the values into the theory, calculated the whole theory in that
Yeah,
data?
they were calculated.
So I think you used some kind of differential equations. What did you use for that?
The
If I'm not
differential
mistaken.
equations were to model the initial flame behavior. This was used derived from the law of cooling and the Rayleigh theorem, and it was used once we measured the accelerated flame, the narrowing trough diameters. We then went over.
I understand.
And
So did you model that numerically?
yes,
And the
like those straight lines. That's
this is like the numerical result from the. And where did you get the values for the input? Because I've been predicting that like in case of this kind of problem would need some kind of literature values for the.
literature varies.
Like did you use any literature values in your theory? Maybe some kind of fit?
Such as A, the A. Yes.
Sorry?
Such as A.
Okay. So this is like using the literature values purely. You have this kind of an agreement.
Oh, no, this isn't literature values. Sorry, this was derived using literature values
Okay, I
for
understand.
certain values in our empirical model.
Those
Sorry.
are- yeah.
But overall, it was derived through.
Okay, but you're just stating, okay, that you got this. Okay, thank you very much. Yeah, I get it. Then maybe let's discuss, or maybe go back to the point of the flame velocity, because I think it's quite important in our case, because just overall about the phenomenon. So what would you say, what are the limits of the flame velocity?
Well, there were several limits as explored in my presentation, such as temperature. This was a really big limit because it impacts the evaporation of the fuels at the track's reservoir at base.
Yeah.
But this was mitigated with, cooling effects and also the new track design. Additionally, limitations were also if the track walls were not long enough, then they
Okay.
couldn't contain.
So maybe just like to shortly say, we have the dependency on the geometrical parameters,
Yes.
and also on the layer thickness, and or just like on the field parameters.
Yes, as I stated in the conclusion.
Okay, would you say that like with the pipette it was sufficient to, because if we say like hey, the flame velocity strongly depends on the fuel parameters, do you agree?
Yes.
Like it's really like important to ensure that we have this consistent layering and so on.
Yes,
So
that's
that with the
why
pipette,
fuel layering was actually investigated.
this is like what you did with your battery tracks side.
Yes, that's why it was investigated to find the optimal.
Oh, okay. Okay, so yeah, I think I agree with you with this kind of optimization where you have the gap for the fuel to go inside is a pretty nice validation for that. We have the same layer height, which in my opinion is also the key problem or key parameter in this phenomenon, especially for the velocity. Maybe going to the problem or like my clarifying question to the experimental setup, we used the 3D printed part, and you mentioned that you coated them additionally with this kind of coating.
With heat protected coating.
Heat protected coating.
That's because the other ones may come in
Exactly. So first of all, even though we have this heat protected coating, isn't like it's do you have like an assurance that the ring didn't deform due to the temperature?
Pardon?
Like due to the temperature, did the ring deform?
I measure temperature with the temperature probe, if that's what you
Yeah, I mean like we have a heating of the ring itself, so like did the ring stay the same, or we have seen like some...
it heated the same. The plastic didn't
I mean like the
fire.
formation and the geometry would also stay the same.
It did, yes.
Okay. I think this white kind of a part should be ensured because I think the temperature and the kind of ethanol burning can influence the ring a lot. You have tried to solve it with this kind of coating. Thank you very much. So first of all, we discussed the flame propagation itself with some kind of conditions for the one's flame to start, as I think it was missed out in the report, and also during the basic explanation, but also clarified in some of the things as most of the experiments were done for this one straight part of the line, which I think is all right for some kind of preliminary measurements, but as the whole task states for the propagation inside of a ring, I think all of the parameter variations should also be done with the ring. Then we also discussed the tracking of the flame and how it was done. It was quite questionable for me that we couldn't see any continuous velocity graphs over time and also see discrete points, which still stayed a bit questionable for me. And also we discussed some of the theory, where I want to say that we've seen a kind of sophisticated theoretical model. Nevertheless, I didn't really understand at the end how it was used in the whole presentation, how it was experimented and verified, what was the slides, if it was solved numerically. Oh, thank you.
Okay, so can you please connect the PowerPoint? I'll ask a question. So do you think that there's Marconi flow that's happening inside? So there's a change in surface tension because it's repeated of the liquid spewing?
Yes, so I think this could be something as a report, because I think we have to change the flame velocity.
Let's go to slide 8. I want to ask for your PDEs, what are the boundary conditions for your PDEs?
The boundary conditions? Well, are you thinking about the percentage of ethanol use?
Not what I'm asking. At the bottom of the trough, is the boundary condition, so basically like...
I'm referring to the surface of the fuel.
Yeah, does it stick?
Yes.
Like contact surface?
Yes.
It sticks. What about the hose that you agree with that?
I didn't really understand what was meant by
The
slipping.
boundary condition. So,
Yeah.
so for the PDE...
Yeah, I think it must be investigated as we see that we have this difference of the velocity over time in this case.
And then for the reporter, so I assume you think this is a zero order of first order chemical reaction?
Yes, it is effectively represented.
And then for, I know that you used a linear track, but for a circular track, have you measured the frequency in which the plane propagates?
Yes.
Because,
Are you talking about the acceleration?
no,
Yes.
the how of the plane, because it's like it's continuous, right? So have you measured the
Yes.
frequency?
Yes.
Can you show me how it?
Okay, so I assume you mean the number of times it passes a point.
Because it passes a lot of times,
Yes,
right? What?
and sometimes the frequency does increase over time.
Okay. And then you talked about there's a few regimes, right, for the plane.
Yes.
So how exactly, are there any diagrams of the regimes? Like, for example, maybe some of them have no
Well,
phase.
there's no flame here.
Yeah, I know, but is there any like conditions for it to be no phase? Have you
Yes, and I presented on them.
where like what are some conditions that show that there's
My presentation is on optimization, so no flame is when there's not enough fuel in the reservoir to sustain it.
And then for the circular thing, have you observed the difference in the speed between the inner radius and also the outer radius? So do they move together or?
No difference was observed.
So the angular velocity is the same?
Yes.
Or the actual velocity?
Yes, you can imagine that the flame is just going like this. It didn't break into two like
And then moving on to the experiment, what is for a reporter, where do you think that temperature approach should be placed in the experiment?
Well, the temperature probe was placed on the outside of the track because it was used to measure the track's heating.
Okay. And then can you go to the slide with the velocity formula? What is A? So maybe the opposer can also answer what is the value of A?
Well, I wouldn't be able to answer you this question.
What about
A is the diffusivity of air.
Okay. Definitely. Thank you.
Recommend the time review.
Okay, so I'm Jaden Moore. I'll be representing Team Hong Kong today to review this problem of traveling plane. So firstly, moving on to the problem statement, we believe that the Team Germany is correct. It's ring shape, so we believe that the emphasis should be on the ring shape. And then we believe that there are three tasks that are identified from this problem. So the first one is to identify the regime, which is with the conditions whether it will actually propagate or not. And secondly is to measure the flame's characteristics, for example, the speed or maybe the temperature versus the parameters, such as like the layer depth, the trough width. We believe that it's somewhat done inside the Australia's presentation, and then also compare the quantitative model from the theory against the data. So not only just trends. So we believe that the last task is somewhat done only, and overall it's just partly completed. So maybe let's start with the report summary, right? So they have quantitatively explained the reaction diffusion equation and also the thermal diffusion, and also the PDE that was in slide 8. And then also they've said about the there's going to be pulses, right? And also the flame front will be passed through the equivalence plane. And then for the theory, they said about the thermal feedback loop, and then they also however, they said that it's going to be an ice bath, but we are not really sure how the theory actually models that. And then for experiments, they have varied a few types. They've varied the trough width and also the field layer thickness. And then some rings are ADS, which is flammable. We appreciate the effort to put heat, some kind of heat resistant things inside, so we believe that the experiment was somewhat okay. And then for analysis, they focused on the measurement of the speed and also the stability of the flame lifetime, and also showing how there will be an optimum point of the thickness of the field. We believe that is well done as well. So therefore, we believe that some of the strengths here is that they have clear definitions of what's going on. They have classified the regimes of some different flame types, and also they have controlled experiments, and also have a somewhat quantitative analysis of the problem. But some points to improve here. So it's so firstly, the Marangoni flow is actually missing. I'll talk about it later. And then basically there's the analysis was not really clear. That, for example, the equation with the A, the physical meaning of A is actually very blurred. And also, we believe that some of the constants inside the equation, for example, in the slide 8, the PDE, it was not really, I'm not really sure if it was taken from literature or maybe it was actually measured in experiments. And then, so moving on, and to the opposition summary. So the opposition firstly asked about the experimental setup inside the questions, and also asked about the lines on the graph, which I believe that the reporting team has answered that they are going to be trend lines mostly. And then, so moving on, we believe that some of the strengths here is that the opposition has actually clarified the cause of confusion and also cleared up our the mechanism, the qualitative mechanism, basically how the thing actually moves forward inside the linear track. So it also has an effective time management because it asks like the important questions first. However, we would like to say that in the analysis we would they spend too much time discussing, for example, the line. We believe that a lot of it can be like repurposed to be on the for example, on how the PD is actually formed and how the velocity is actually calculated from the equation. This is like one of the major points that are missing in the presentation. So the first clash here is on the rectangular track. We agree with the opponent here that rectangular tracks were used too much in the report. We believe it should be ring-shaped as thick as the problem segment. And then for the velocity measurement, the opponent thinks that there will be parallax error, and also like there's the average velocity versus time. And we agree with the opponent here. The velocity should be tracked over time, and like they have not really explained whether the acceleration actually changes, right, for the reporter. And then for the theory line, the problem of theory line, the opponent thinks was thinking about whether the literature values were actually used. We agree with the opponent here again that the opponent has actually clarified some of the confusion about how the theory line is actually formed, and while some are actually trend lines, right? And then for the track material, we agree with the opponents here that the ADS is actually like kind of a big issue here because ADS is flammable, and we believe that some other forms of like maybe CNCing aluminum ring will be much better for the phenomenon to form. And therefore, here are some of these points. We believe that Marangoni effect is one of the core mechanisms because it preheats the liquid in front over the evaporation point. So therefore, there's a greater rate of evaporation, and we believe that is very important. Thank you.
Would you like the report to come up and to the next round?
So, in conclusion, I've given a qualitative explanation of what conditions are required for the flame to propagate continuously. The majority of my report was on the optimization of these parameters, included on geometrical and fuel from both qualitative and quantitative data and phenomena regimes, which I explained. On the points from the opposition regarding my admission process, we experimented with different flame restriction tools, but due to experimental restraints, rectangular tracks had to be designed actually to investigate the phenomena. Otherwise, the flame would just go in two ways instead of one, and we had to rely on imbalances in the reservoir, which would cause uneven heating, and the effect of heating has also been explored in my presentation. As well, they stated that there were problems with using a theoretical model proposed from Croatia's IYPT team. However, we believe it is important in the experimental process to adapt ideas proposed by other researchers. The parallax error to derive velocity was clarified as I showed the some sort of wave graph. That was why I showed that earlier. And using tracker software, because it actually does appear as a sinusoid wave. Regarding the ring-shaped track, they asked why variations were done with straight line track, and yes, and we replied it was necessary to use rectangular tracks. Regarding the heat protective coating, these 3D printed tracks were coated using heat protective coating, and actually the heat protective coating filled in the gaps from the plastic, so it had the opposite effect that they proposed, which is it would cause an unstable gradient in the reservoir. It actually filled in the gaps, as you can imagine from the paint.
Thank you very much. Okay, now three, people now, please. Just under, yeah.
Maybe first question to the reporter. What about flame height?
Flame height?
Yeah, so when my flame be higher.
That was not investigated in the phenomena. However, it was observed
have to make a guess how can you make the flame higher?
How could I make the flame higher? I would guess that narrowing the walls to the extent where it doesn't quench the flame, but there is sufficient fuel in the reservoir to sustain, so 100% ethanol, I'd say, or even a more potent fuel, and also narrower trap walls.
Do you agree?
I would say we could just achieve it by making the walls higher, as the gas can only be escaping that much, and as a result, we could also achieve a higher flame. But I think it's overall that relevant to the phenomenon of the motion of the flame itself.
I would like to disagree with this.
We're not having a debate. Are there any questions?
Can you please go to slide number 23? In the meantime,
Okay.
How do you think Marangoni effect is relevant?
So basically, because
Sure.
the flame preheats the liquid in front, and the increase in the temperature, basically, the increase in the temperature increases the surface tension, so there will be a bulging of the liquid in front.
So it will have an effect on the speed of the...
I think it does, because then there will be, I believe there will be increase. Yeah.
Here is a quick question that I'm not sure if I understand these lines. So for instance, they do not cross the 0 point. Where does it come from? Is the V0 a heating parameter in this regard, or is it not visible?
Oh, the V0 is the initial velocity of the flame, so that was experimentally obtained.
And the lines, they must take line to the experimental data.
No, they're derived from the zero.
And that gives you a straight, a military straight.
It should actually be an accelerating line, however, an exponential line, however, I don't know that using the technology, unfortunately.
Sorry, what did you say?
I couldn't model it.
You couldn't.
But
Okay.
it's,
Just the last thing. I can see one line like a pinky purple colour. So
Yeah.
I can't see on the rough diameters. Is there a colours or
Oh.
a
so sorry, I should have extended that. There's actually, there's another one I just forgot to put it on there. That's my apologies. But it would be the thickest diameter.
Okay.
Then it tends to be air foundation.
I think.
Then you tend to go air foundation.
No, these were single flames. So these were single flames. Yep, at a point.
So you mentioned like declaration theory. Well, when did you get it? I just wanted to clarify from Croatian team that you guys.
Yes.
I just want to.
Oh,
Can you clarify that? Like watching back at what.
Okay, so at the end of their presentation, which they published online as a PDF, they had actually proposed this theoretical model because they had explored tracks that were just straight wall, but they proposed
But
this.
like it was just like this. You got to see it now.
No. Sorry. The IPT team from last year.
Okay.
Yeah.
Good. Thanks. Yeah.
They did it last year.
Yes. It was for IPT, not IYPT.
Okay. Can I just check? With review, you mentioned the ice bath.
No,
Was there a mention of an ice bath?
no, I think it's just a cooling mechanism. I was saying. Yeah.
So you realize that?
No, I said that the cooling mechanism, it may have an effect as well.
You just had ice bath. So, thanks.
One last question. Is it possible to have two flames if you ignite on opposite side of the ring?
Yes.
What happens if they catch each other?
They extinguish. If the flames are both traveling this way,
No,
then
they
they're just.
travel in the same direction.
Oh, that is possible, yeah. But you need to have fuel replenishing at a rate that will allow it to be doubly propagating.
Okay, thank you very much.